All right, everybody. So we've talked about the interior of the Earth, but let's talk a little bit about the crust. So the crust, where we live, is constantly changing by lots of different mechanisms. But I want to just talk about one today, and that's plate tectonics. So as the crust cooled, of course, it was much more uniform in the past, and now it's got all kinds of mountains and valleys and structure to it. And that was all created by plate tectonics. Now, some of the way those structures have changed over the years has been caused by other things like erosion due to rivers, etc., and the wind and all kinds of other processes, which we'll talk about later. But let's just talk about the big things: how did mountains form, ocean ridges and valleys, and we'll talk a little bit about volcanoes as well. All right, so first let's look at a video. So let me get out of this and we'll go to our video. That is right here.
Okay. The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on, unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental landmasses, the thinner of the two plates bends and slides under the other. As the edge of the seafloor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
Okay, so pretty interesting. Let me kill this so it doesn't start playing something else. Okay, let's start our slideshow up again. All right, so as you can see, the plate tectonics is actually quite complicated and is the origin of a lot of different, they didn't really talk about it in the video, but a lot of different things that we see on the crust of the Earth. Okay, so for instance, as you could imagine, if you are if there's what's called a little hot spot, so we didn't really talk about hot spots. Again, we're going to go more into volcanism later, which is the study of volcanoes. But imagine you have a hot spot, right? I mean, remember, this is this molten rock from the mantle, not from the core. And it is sort of a hot spot poking up through the crust. It can actually create land so here's the sea level, as the rock comes up out here and cools, right? So as you can see, this actually can actually make an island, and this is actually what people think are the origins of the Hawaiian Islands, and they also think that there is another island being formed where the where this hot spot is creating more land under the ocean. It's not the island has not popped up and probably won't for tens of thousands of years if it actually is happening. There's some evidence that it is happening, and people have actually already named it Loihi, and is this another of the Hawaiian Islands? Of course, it has not broken water. It's about, people think that the highest point is about 3,000 feet below the surface of the water right now. But we think that is how, certainly there's a lot of evidence that that's how the Hawaiian Islands formed, was that a plate moving over a mantle plume where it's moving very slowly, and it creates, one island and then another island and then another, and that's the chain of islands we see in the Hawaiian Islands. And again, there's another one coming, we think. Okay. Now, on the ocean floor, there's, you can see two plates moving apart can cause these ridges, like they were talking about in the video, where the molten magma rises and sort of makes new land as these plates are sort of spreading apart. Okay, and of course we all know, you probably learned this in either high school or middle school, somewhere where you did earth science, that all the mountain ridges that we see, all the mountains were formed by plates coming together, not spreading apart, but coming together, kind of crashing into each other and pushing land up on the continent. So this wouldn't be under the ocean, but this isn't the formation of new lands like in the islands, but two plates colliding, where you now just colliding in this place where you have land, not ocean, and creating a mountain out of that crash. All right, let's pause the video and try a question.